Hello and welcome, this is the experimenter, and today we are here with one of the craziest integral that I have ever seen in my life. The integral goes on something like this. The thing that is to be integrated is x to the power dx minus 1. But before I dig into this, I would like to show you some basic concepts of integration, or you might say the basic principle of integration, and after that we will go into this. So I'm drawing the graph of an arbitrary function which you can call f of x, and I'm limiting it by two arbitrary variables a and b. Not variables, actually they are limits. Limits is a good word, but what I meant to say is you can take any limits. So this is it, and now what we are doing is we are dividing the whole area under a and b into smaller rectangular strips. The width of each strip equals to b minus a by n. So let us show that in the graph itself. This might not look like rectangles, but they are, at least mathematically they are rectangles, and width of each rectangle is b minus a by n. Now suppose if I now ask you to find the area, you might just understand that the area under the function from a to b is equal to the sum of the area of the rectangles. So let us just represent that mathematically. Let us take an arbitrary point k, and the value of the function at that point is f of xk. The point is xk. I might have misprint. Yes, I have written k, but that should be written as xk, and the value of the function at that point is f of xk. So the area, so the kth rectangle has area f of xk into del x. Del x is the width, and so we can write the total area of the function under a to b as summation of f of xk into del x, where k is varied from 1 to n, where n is the total number of rectangles. But this is not perfect, right? Because n might be very small. If I just divide the area in two rectangles, of course we are not going to get a proper estimate. So n should be very, very large, and so that del x should be small. Now we are just redefining that area concept which we have written over there. So we are writing area as limit n tends to infinity, summation of k equals to 1 to n. Here just see the change. We are just adding a limit which tends to infinity, so that the width of the strip reduces to a very, very small dimension, and the rest of the thing is just like that. So this thing, the one in the yellow, is equal to a to b f of x dx, which we are aware of, which we have done earlier in definite integrals. So this is just a short proof of the function, the area of the function, which is actually the definite integral under certain limits. So the reason because of which I stated this known fact is that we want to re-verify that dx should be as small as possible. Now let us see why this is important in evaluating this integral. If dx tends to 0, we can write the integral as x to the power dx minus 1 whole divided by dx into dx. Now see that orange marked portion. It says x to the power dx minus 1 by dx, and it is very similar to one of the standard limits. Let us see how we are approaching the problem. If I see the marked portion, it says x to the power dx minus 1 by dx. Now just for the sake of convenience, I'm substituting dx by n, so we might just write limit n tends to 0. Yes, n as dx we are taking. This whole thing reduces to x to the power n minus 1 by n, which we can see is in 0 by 0 form, which is indeterminate. So what we need to do is we need to differentiate the numerator and denominator once, and let us see that whether that becomes a determinate form or something solvable form. So just differentiating, we in the numerator we get x to the power n log of x, and denominator we get 1 if we differentiate with respect to n. The limit n tends to 0. So this whole function x to the power dx minus 1 by dx gets transformed into log of x, more specifically log base ex. So now we are left with log of x, because x to the power dx minus 1 by dx is actually log of x when dx tends to 0. So basically this is nothing but indefinite integration of log of x dx. So here it is, and we know we are integrating by parts. By integrating by parts we get this. The whole integrand reduces to x log of x minus x plus c. So what I wanted to tell you is this integral is pretty weird, but one thing, the very fundamental theorem of calculus is needed to solve this problem. We need to know that dx is very small, and because dx is very small, this limit exists, and that is why we can actually evaluate this. Thank you.